This is what I reconstructed from a phone video using AI, 170,000 hair strands. It is incredibly realistic. Then, through a secondary AI conversion, I converted it into hair cards that can run in real time. Hello everyone, I'm Fan.
I'm Xiaoyao.
Today, we're going to talk about how I used AI to generate 170,000 ultra-realistic hair strands, and how I used AI to turn it into usable game assets. First, let's talk about hair in games, and why current AI-generated hair can't be used directly in games. In 3D, hair mainly comes in three forms. First is the mesh tube, where the hairstyle is modeled as a single solid geometry. It features a low polygon count and quick production time commonly seen in mobile and stylized games. The corresponding downside is the lack of strand level detail. So, to recreate this strand level detail, the second type of hair is hair curves, simulating the roughly 100,000 to 150,000 strands on a human head. Rendering this structure can yield an extremely realistic hair appearance. Of course, its computational cost is extremely high. This is no problem for film-level offline rendering, but what about for games?
It is way too laggy,
making it difficult to achieve real-time interactivity. But as of today in 2026, the latest mainstream AI reconstruction in academia still primarily outputs hair in the form of hair curves. Let's bring it back to a more practical scenario. In games, we want realistic hair textures while also aiming to achieve fast rendering. That brings us to our third type of hair representation. It is a plane with an alpha channel, using just a small number of these planes to simulate the visual effect of a lock of hair. Then, relying on the skilled hands of our artists, through proper texture mapping and geometric arrangement, and spending a massive amount of time, these hair cards can effectively recreate the intricate structures of complex hairstyles, making them look incredibly close to real strand-based hair models to the naked eye.
Crafting this entirely by hand is pretty time-consuming, right?
It is very time-consuming. So that means our goal is a production-ready game asset, namely hair cards. However, current mainstream AI reconstruction still outputs a massive number of hair strands. This explains why existing AI-generated hair cannot be used directly in games. That is why in 2025, two papers were presented simultaneously at SIGGRAPH to solve the problem of converting hair curves into hair cards. Before that, when we talk about converting hair curves into hair cards, we first need the raw material. Where do these hair strands come from? After all, the quality of the hair strands determines the quality of the hair cards. In the last episode, I used the AI generative model Deflux. By inputting a single image, it can generate the corresponding hair strands in just 30 seconds. But the problem is, it can only see the side visible in the photo, and the hair at the back is entirely imagined by the model itself. So what does this lead to? It performs pretty well on simple hairstyle, but it basically fails on complex ones. So today, I'm bringing you the first big reveal, a solution that can truly reconstruct every single hair detail. Let's take a look at this photo. I was honestly moved when I first saw it. It is so natural and true to life. So next, let's briefly talk about why MonoHair is so impressive. First of all, the input for MonoHair is no longer just a single image. It is a monocular video. Most importantly, it breaks down hair reconstruction into two parts, the inner layer and the outer layer. Let's look at the outer layer first. This is the hair we can actually see in the video, and it has a ton of detail. It uses a module called PMVO, their self-developed module, to optimize it from multiple angles. It takes every frame in the video and processes it directly using traditional Gabor filters. This step doesn't rely on training data. It is extracted directly from the images. This gives you the outer shell, but the inside of the hair is hollow, so you still need to infer the inner strands to fill it in. But the hair inside is completely occluded, the part that is never visible. So for this part, relatively speaking, the requirement for detail is much lower. This is when the neural network finally steps in. Specifically, it takes the newly reconstructed outer hair and re-renders strand images from 16 fixed angles. Then it feeds these images directly into the network, to let the neural network infer the internal 3D orientation field. Finally, it merges the outer and inner parts. That is how the 170,000 strands are generated. As we can see, its logic is completely different from DeepLock's. DeepLock is a purely generative model. The back of the head is invisible, so it just fills it in based on what it memorized about hair during training. MonoHair, however, tries to compute directly from the images, leaving only the truly uncomputable internal structures to the neural network. That is why its details are so rich. And look at how massive the data size is. After processing just one video, it is already 5 gigabytes. Running the full inference took nearly 6 hours. And during the process, I found its hardware requirements are significantly higher than DeepLock's. When I first ran it, I sampled 160 frames as in the original paper, and it immediately ran out of memory. Then I reduced it to 80 frames, and split what was originally a single step into 2 steps, just to get it to run successfully. Then I wrote a script to export it as an ABC file, which ended up being around 200 megabytes. Now we can convert it from hair strands to hair cards. Currently, the most well-known in this field is Tencent Lightspeed, with their auto hair extraction presented at SIGGRAPH 2025. The results look incredibly good, plus it is backed by a major tech company. I was already rubbing my hands in anticipation, but they didn't open source it. So I had no other choice. I could only try to reproduce the paper myself. But just when I hit a dead end, a new path suddenly opened up. I found another paper from the same year. Another SIGGRAPH Asia 2025 paper called Strands 2 Cards tackles the exact same task, and they even open sourced it. After reading it carefully, the two methods are actually very similar overall. But here is a bit of a side note. When comparing papers by students to those from big tech, the impact just isn't comparable. Even though this project is open source, it still only has a 2-digit star count. It is such a shame. Here, I'd like to thank Kenji from the University of Tokyo. Thanks so much.
Nice.
So I pulled the code and ran it that very day. The environment was actually pretty hard to set up. The hardest part to install was NVDFirst, NVIDIA's differentiable rendering module. Alright, let's take a look at the results. This looks pretty good. Kinda interesting, huh? Let's briefly talk about the algorithm. It is also divided into 2 stages, which actually aligns very well with human intuition. First, in the initial stage, it generates the hair strands. Basically, it figures out roughly how many locks of hair there are in total. This method basically uses k-means for clustering. The features used for clustering simultaneously consider both the root position and the overall shape. Strands with similar flow and nearby positions are grouped into a single clump. Then, within each clump, the longest strand is selected as a guide hair. Then, using linear blend skinning, we straighten this group of hair strands and map them into UV space. Next, we use orthographic projection to render opacity and normals and its texture maps. The second step is to optimize the shape of this hair card to match the 3D volume of the hair clump as closely as possible. Now let's take a look at the results without applying textures and just looking at its shape. It actually almost perfectly restores the flow and volume of the hair strands. Now let's add the textures. We can see that the alpha map is generally correct, and there's so many textures for these hair strands. But there are actually still some issues. If we take a closer look, we can see that for this hair card near the edge of the scalp, the alpha is not accurate enough. The scalp shows through. But the boundary of the hair card itself is the hardest place to align textures. We can leave this to be fixed after putting it on the character model. Now let's test out how this hair card looks. I made a little game. I chose myself as protagonist. Here, I first used AI to generate a chibi version of my own IP character. Then I used Triple High to generate this 3D model. Here, I tried out its smart generation feature. I found that it can directly output low-poly models optimized for games. The topology is incredibly clean. Now we have the character and the hair cards. The next step is to put them together. When working in Blender, we can clearly notice that near the scalp, there is an issue with the alpha channel not being accurate enough. But for NPCs that are further away in the game, we can just take the scalp part and paint it the same color as the hair. For the color, I chose pink. I've always wanted to dye my hair pink. So let's just paint the scalp pink. This way, even if there is some edge bleeding, it looks flawless at first glance. And then we're done adjusting. Export as GLB and drag it into golden. It works right out of the box. No errors, no glitches. The hair is right there, exactly where it is supposed to be. We used to say that hair in games was something artists had to place strand by hand. But now, AI can generate it directly. Even though it is still quite rough right now, we can see that this path actually works. This is part 2 of our series on building a complete character pipeline using AI. In the next episode, I want to tackle the biggest limitation in this pipeline. Right now, our input still have to be a video of real hair. So for the next episode, I want to try starting with an AI-generated hairstyle sketch to skip the real-life filming and directly generate high-quality hair strands and then convert them into haircuts. Alright, that is all for today. If you found this helpful, please like and follow us. See you in the next episode. Bye!